So good afternoon, everyone. Apologies for that slight technical hiccup. Welcome to today's Power and Heat Boost webinar. This is a third of a series that we introduced at the end of April. We had one in May, and today is the third of the series, and we plan to continue for the foreseeable future, providing an opportunity, a platform to speak about cogeneration in the context of the many things that are happening here in Brussels in terms of the European Green Deal and how cogeneration can support those aspirations and goals moving forward. Today's Power and Heat Boost will focus on the Renovation Wave. We expect that to be published by the European Commission in the third quarter this year. And today we'll be focusing on how cogeneration will bring benefits to businesses, citizens, as well as the climate. Just for your information, everyone is muted upon entry and will remain muted. Today's webinar is recorded, so for those of you or your colleagues who could not participate in today's webinar, will be able to access it freely via the COGEN Europe website, the Power and Heat Boost web pages. Please use the chat function to ask questions. Or what we plan to do is we will go through the different presentations, and following that we will have a Q&A session. After that, my colleague Alexandra will provide a wrap-up from a policy perspective. So next slide, please, Alexandra. Before we begin, I just want to give a quick overview of the different speakers. So following my short introduction, Olivier Bukeli from Solid Power, who's also the chair of COGEN Europe's MICRO-CHP Vision Working Group, so representing all the different companies and technologies. And then we will have 3 case studies, success stories, one focusing on district heating using green hydrogen from a cogeneration perspective. We have a speaker from 2G, so Stefan Knepper. Thank you for joining us. Then we have a presentation about stationary fuel cells for green buildings, and that'll be presented by Gunther Roche from Senatech. We're very happy to have him this afternoon, so welcome. And then finally, we will have an interesting presentation looking at both cogeneration and heat pumps, a win-win solution for Skole in Denmark, and that'll be presented by EC Power, Christian Neuve. And then, as I mentioned before, my colleague Alexandra will give a wrap-up and look at some of the key principles that we need to ensure in order to have a successful renovation wave. With that said, next slide, please. Just a very short introduction to COGEN Europe for those of you that are not familiar with the organization. We are the Brussels-based European Trade Association representing the views of the cogeneration sector. We primarily work with the EU institutions, so the European Commission, the European Parliament, and the member states vis-à-vis their permanent representations in Brussels, and also with our national associations and their capitals. Next slide, please. Here is a quick overview of the members of COGEN Europe. We're a hybrid organization. We have national associations, so 12 different national associations across Europe representing cogeneration. We also directly represent many of the companies themselves or organizations that are involved in cogeneration, from the small, so from the 1 kilowatt all the way to the megawatts, from the manufacturer side, the OEMs, but we also have companies representing utilities, ESCOs, and we also have many end users. That makes the organization rather unique in the sense that we represent the entire value chain of the cogeneration industry. Next slide, please. So that was my bit as an introduction, and I will now give the floor to Olivier, who will give a further in-depth introduction on cogeneration and its role in providing efficient and clean energy for buildings, for citizens and businesses. And so, Olivier, the floor is yours.
Thank you, Hans, for a kind introduction. My name is Olivier Bucheli from Solid Power, acting here both as a Vice President for the MICRO-CHP part within COGEN Europe, but also in an active role for the stationary fuel cell. I'm the technical committee leader of Hydrogen Europe for stationary fuel cells. And in this respect, converting the technologies also in future covering hydrogen gas turbines, for example, in application. That's on the overall part. Now, we want to bring in here the focus on cogeneration. Independent from the fuel that we use, cogeneration has its advantages and in terms of primary energy savings and emissions reduction overall. Now, what is the role of cogeneration in the terms of buildings, or what role do buildings play in the overall energy consumption and world? So we have on the one side 30% of the energy consumption in Europe is based on buildings, and buildings are responsible of 36% of the overall CO2 emissions within Europe. So it's a significant sector, and any savings will be directly reflected in overall balance. What is also important to understand is that the current built buildings are 75% are inefficient, meaning there are heat-saving methods that could be applied to, but we have a very slow renovation rate, normally below 1% a year of annual renovation. And also we have, compared to other continents, a low building replacement pace. So 90% of today's building will still be standing in the year 2050. Based on that, we need to understand that renovation has a role to play, but not only renovation in terms of modifying the building structure. There is also cases where it's very difficult to get energy savings in a building where efficiency in the transformation of energy can directly, within the build stock of buildings, provide added value. And this is, of course, the very important point for cogeneration. So if you go from, yeah, please stay on this slide. Thank you. This one, yes. Now, will you go to the other slide, please? Yes, thank you. Heating and hot water is basically 80% of the overall household energy consumption. It's a very important fact. And the remaining 20% normally is electricity. So that's the proportionality that we need to understand. So the 20% of electricity usually is provided through the electricity grid. And from the grid side, it is considered to be easy to replace or easy to move from fossil to renewables. This is to some extent possible, but in reality, we have also the limitation of nature. The dark doldrums are also affecting that. But it's very important to understand that the heat and hot water demand is representing 80% of the overall household energy. Furthermore, the construction sector is 9% of Europe's GDP and has a significant amount of jobs associated to it. More than 1 million jobs in Europe are directly related to the construction sector. So buildings are central in Europe's energy world. They have a high impact. So this is one part. Now, please move to the other slide that you had shown before. There is also important to understand that in the wave and trend of moving from the classical fossil generated electricity to the renewables, the system has fundamentally changed in philosophy. So from a centralized point of view, where you have also economies in volume, so the larger you build a plant, the higher the efficiency is. That's why power plants of 200 megawatt or 1 gigawatt are built to benefit from those economies of scales in those power transformation processes. From there, this goes to the high voltage grid and this distributes downward. This was 20 years ago our reality. At the beginning of the year 2000, basically, also pushed by Germany as leading country in terms of subsidizing both PV and wind, we have seen changes occurring in a first step that the grid had to become bidirectional. and not only from generation down to the end user, but also the end user becomes partially prosumers because they start to generate their own electricity, or we have also electricity generation in the level of a few megawatts to tens of megawatts also connected to this grid, increasing the overall complexity a bit. So this is the decentralized scheme. And nowadays we understand that to get a grasp on the full potentiality that is behind this, we also see that the distributed generation, the virtual power plants start to be applied for, which is also offering new business opportunities to cogeneration, for example, complementing it directly with the renewable energies that are intermittent in nature. But often we have overlap in terms of electricity demand and heat demand, which is a favorable use case generated for the cogeneration use case. Now, this, what we see here on the slide, is what has been happening over the last 20 years from centralized power electricity generation to a distributed one. And what we also start to see, we just on the glimpse of it, the start of it, the same thing is about to happen to the gas grid. The gas grid is also getting decarbonized, partially on a megawatt level from wastewater treatment plants that have biogas or biomethane, basically getting re-injected into the grid. But we start to see what is have on the right side. We have also the power to gas with the hydrogen injection into the gas grid, where we see experiments and demonstration being produced, for example, in Italy, up to 15% of hydrogen injected for the use in a pasta factory close to Napoli. We start to see this also happening on this side. So again, increasing complexity on the one side, but presenting also a means of decarbonization of the gas grid that is important. So you could also call it an electrification of the gas grid if you go then for the power to gas, or in the use of the biomass is of course also a very nice case, because this biomass is just exploited in a proper way and allows the storage of the molecules in the grid to be used whenever it is required. So this is a complementary move that we will see and observe over the next likely also 20 years to become material in our daily reality. So next slide. So if you look then at the overall balance of the different heat sectors, so we have of these different energy vectors, it's important to understand that the heat is representing a significant amount and of the overall energy demand. And this energy demand of heat is not evenly distributed. It is clearly, we have the high heat demand in the winter period, and this is also the period where at least the photovoltaic sector is weakest in production. We have approximately 70 to 80% of the photovoltaic electricity produced in 3 months of the year, basically May, June, July. That's the one thing. And the rest of the electricity is produced over the other 9 months, with the low basically in late December, 21st December, of course, with the winter time and little solar. Fortunately, there is a bit better profile for the wind power that sometimes has a higher profile in the winter period. Still, it means that while it is rather simple to electrify or to decarbonize the electricity during the summer period, in the winter period, we have a complete different footprint on CO2 in the electricity grid. And if we're going to electrify, just in terms of proportionality of the energy needed to go through and getting distributed, we would need, even using heat pumps everywhere, we would need a triple capacity of distribution of electricity to all the buildings. This is just from the aspect of the distribution. And we would still double in the overall year the overall electricity consumption, which is very, very significant. So we need to understand what the implication is if we move to an electron-only based system. The electrons are difficult to store. We know we can store them in batteries for a limited period of time. It's perfect for a day-night cycle. It's challenging for an annual cycle. And in this respect, the system, the energy system, clearly needs to have 2 legs to move forward. Please, next slide. So in the current situation, you have here on this slide illustration of the different volumes. We have the low-grade heat. This is basically the heat that goes into building for either comfort in the house or for hot water. So we do not speak about process heat in the industry, but only the low-grade heat. And we have the electricity demand. Throughout the year, the electricity demand is rather constant. You have some smaller peaks during the week versus the weekend, but this is basically the blue line that you can observe, or the blue cloud going through. Then the red peaks, you see the heat demands that are really peaking, and those heat demands are, the peaks are determining how big an electricity cable would need to be. Now, if you compare the power density, the physical power density of a cable, electric cable with a gas pipe, you understand that then afterward, a gas pipeline has a much higher capacity to transport energy to the end use, the point of end use. It's in the nature of the molecules versus the electricity. So electricity is easy to distribute in a short range. Over longer distances, it requires significant amount of space. And from that point of view, it's clear combining both energy vectors is very important. And we also need to understand, if we add in the current existing electricity scheme additional consumers, we need to increase the capacity of the electricity production. So it's not for free. It is not that we right now would have sufficient available electricity to electrify the heat in the winter period, because this electricity is already used up. In summer period, it might be a bit different, where we have an excess generation of electricity through the renewables, through the solar peak, but it is not properly absorbed by the market, and therefore we have the options of the power to gas that is considered in this way to flatten the peaks. So next slide, please. Yes. Now, what is the role of cogeneration into that? Cogeneration is with a single input, which is a molecule. Can be biogas, can be natural gas, can be hydrogen. We have two outputs. So a primary energy is transformed into two final energies. One is the heat and one is electricity. And the nice thing about cogeneration is that those consumption peaks are occurring at the same time. So if there's a heat demand, we generate the electricity. And this electricity demand today, in today's energy world, we have also an electricity peak occurring from often also heat, electrified heat, like a heat pump, which is basically an efficient electrical heater in this respect. So what it's transforming electricity into heat and extracting some of the heat from the environment. So we are basically perfectly complementary with cogeneration, as whenever the heat pumps produce a peak on the network due to the heat demand in the buildings, cogeneration is providing the heat to its local building, but also providing the electricity to this building at the same moment in time. And this is a complementarity that the proportion of heat pumps and fuel cells should be adequate to have savings on different levels, and I will come to that in the next slide. So basically, we have the overall output transforming the molecules into end use is 90%. This is a high value if you compare it to traditional means of transforming the fuel. In the centralized thinking, you have on the one side, this is on the upper slide, part of the slide you see it, you transform fossil fuel, or you produce the energy, primary energy, into electricity, and you have a lot of waste heat that you need to even to pay for to get rid of it. And you have another dedicated flow of fuel transformed into heat only. So in terms of exploitation, this fuel could also produce electricity at the same time. But in the traditional case, you just make heat out of it, and you also have some additional losses. So out of 100% of primary energy, you make 56 final used energy. Now, if you do cogeneration, the same process, a single process, provides you both at the same time electricity and heat. And that's the key for it. With this combined generation, you do not throw heat away at one side that you need to generate at a different side. But you have the local production and the distribution within the buildings to have out of 100% of fuel, you get an 80% useful energy. So it translates basically in up to 40% of energy saved overall. And we have calculated at 30 to 50% CO2 reduction, depending on which country and the footprint of electricity in the country, of CO2 emission reduction, which then, of course, reflects in a reduced energy bill. Next slide, please. Within Europe, we have several cogeneration technologies. Overall, we have 100,000 micro-CHPs installed in buildings, and more than 10,000 are stationary fuel cells. This is the recent technology that is now started to be implemented at a bit larger scale. And COGEN Europe has a very active role in two deployment projects, which is basically Ennefield and PACE. And in this respect, we see forward to the cost reduction achieved through those projects to have a further deployment. So, but CHP can also be applied not only in residential sector. The more common one is CHP also to feed district heating networks or larger public buildings. And finally, in the industry, combined heat and power is a quite standard technology for many applications where you have a continuous need of higher amounts of heat. You also exploit electricity generated locally. Next slide, please. So what is important when you go to micro-CHP to understand is micro-CHP generates electricity not all through the year, but at the moment where the intensity, carbon intensity of the grid is, electricity grid is highest. So it is generating the electricity when it is needed, and normally also when the renewable energy already is used up fully, and where the dirtiest ways of generating electricity is needed to apply to keep the overall electricity system stable. That's important to understand. So it's not displacing renewable electricity, it is displacing the dirtiest electricity. This is out of the marginal calculation of carbon intensity that we see, and it's important that this factor is complementing. So if you install additional heat pumps in the current scheme, you increase the use of the dirtiest electricity generating devices, and it's the ones also that are displaced by the fuel cell or the micro-CHP appliances today. So this is why there's this complementarity in the field. Next slide, please. Out of the studies that we have pursued, we see potential for micro-CHP uptake up to 31 gigawatt by the year 2030. Important to know and understand is that producing the electricity locally, very close to the end user, this means at the same time we avoid grid enforcement costs. We avoid grid enforcement costs on the one side in the low voltage sector. We are producing the electricity at 240 volts in the customer's house, but you see also other effects in terms of the medium and the high voltage grid that are still significant, because the gas infrastructure still allows to have an more extensive use. The gas infrastructure is higher in power density and has already been built for a long time. There are significant reserves available to distribute and generate this out to the end user. And deploying micro-CHP at a large scale, it provides the option to have up to 28% of EU's projected grid reinforcement needs to be covered by micro-CHP. So it means that it frees means you don't need to have a long-term investment in the large electricity infrastructure that, besides the cost, also has an issue in terms of speed of deployment. If you look at how many kilometers of high voltage lines have been built in Germany over the last few years, you're afraid that you see it's not possible to progress at this kind of steps, but you can make best use of an existing infrastructure already today by micro-CHP, by cogeneration in houses. Next slide, please. So what does micro-CHP do overall, or cogeneration overall? it is linking the different sectors, creating an arbitrage between the electricity, heat, and gas systems. This, on a system level, is improving the overall efficiency. It's very important. It is not wasting the heat out of an electricity generation process, but directly using it. But it's also compatible to the use of, for example, excess electricity under the form of hydrogen or biomethane, or cogeneration in other district heating cases often uses lower grade biomass to directly generate both the heat and electricity locally. MICRO-CHP are small plants, so they provide flexibility to the grid, dispatchable power, and overall they lower the energy system cost. And also important, wherever you have those systems, they need to be maintained and installed. This is local job creation, a distributed way, and not at a single large power plant. Next slide, please. Next slide, please? You have an issue with this slide? Or is it my screen that is frozen?
We are on slide 16 at the moment.
Okay, I am on slide 15 in my screen. That must be my screen. I apologize. Okay. Oh, now it changes also. Yeah, okay. So, what does cogeneration provide for overall? It cuts carbon emissions already today with the installation and reduction in the primary energy, and it's forward compatible to the reduced carbon footprint from the gas grid. It lowers the energy costs at the end user by the reduction of the primary energy usage. It is integrated with renewable energy vectors, and overall we have energy savings. Important as well is it empowers citizens and businesses. It creates autonomy, and the local energy production is helping to create and stabilize the overall grid. It provides the flexibility in terms of balancing with the different schemes of electricity production that are intermittent, so stabilizing overall, and it is clearly reducing the cost of additional grid reinforcements generated by both one side on the peak generation capacity of the renewable electricity, but also on the peak load side in terms of the increasingly electrified heat production. So overall, it is a balancing factor. It combines the different elements to enable overall in the system an optimal solution. And those values are the ones that need to be recognized. And with this one, I would like to hand over to the next speaker for illustrating the cases.
Thank you, Olivier. I'd like to introduce the first of our three speakers, so Stefan Knipper from 2G, who will present a success story case study in the case of green hydrogen cogeneration use in district heating in Germany. The floor is yours, Stefan.
Yeah, can you hear me?
Loud and clear.
Yeah, okay. Thank you, Hans, for your kind introduction. I'll start my presentation. Oops. So, you see my presentation?
Yes.
Yeah, okay, thank you. So, let me introduce myself. My name is Stefan Knipper. I'm working as an R&D engineer at 2G in Germany, and we are developing gas engines running on hydrogen. And today I prepared some slides for you for the project of the city of Haßfurt in Germany, which has a hydrogen CHP with electrolysis. So first of all, let's have a look why we think that it's a good idea to use hydrogen in CHPs. On this slide, you can see a chart which shows the excess power in Germany on the time of one whole year, so from January to December 2019. And we can see there are high peaks with excess power where we have more power capability than we need, and we have low peaks also. But there are also wide ranges where where there's too less power, and wide ranges in the summer, for example, where there's too much power. And the reason are mostly the renewable energies which are fluctuating, especially wind and sun. And we think that it would be a good idea to use the renewable energy power to produce hydrogen, to make a shift of these energy to the times when we need the energy. So how could such a system look like? Of course, the source is always wind and sun. These are the renewables. And of course, it makes sense to use the electricity if it is needed for homes and industry. And for the peaks, we can use a battery storage. This makes sense. But to use it for the long term energy capability, we can produce hydrogen with power to gas plants. And this hydrogen can be used in two ways. The first way can be methanization, so we can use it in normal CHP and put it in a gas, so we can store it in gas storages for natural gas and use it for normal CHPs. This can also be supported by biogas plants. And the second way is that we use this hydrogen directly for these CHPs. So this is what is done in Haßfurt. Let me introduce you to the Haßfurt concept. Haßfurt is a small city in Bavaria. The local utility, provides energy for about 20,000 inhabitants, and they are very innovative concerning CHP, microgrids, and district heating. And the power sources are, you see my mouse. The power sources are wind power and photovoltaic. They have about 31 megawatt wind power and 10 megawatt photovoltaic. And in addition, they have a biogas plant with 2.3 megawatt. And these energy sources are now combined for use in their microgrid. They installed power to gas unit, which is producing hydrogen, and they also installed a battery storage for the short-term energy supply. What you see in red is already in operation. This is existing, and the blue parts are actually under constructions and project plans. But the hydrogen CHP is already in use, but it's as it is a research project, here it's still marked as blue. Okay, now let's have a closer look at this area, so the power to gas and the hydrogen CHP. Here we have the wind power plant, and the excess power of the wind power plant is put into an electrolyzer from Siemens, which is shown here on the right side. It's a 1.25 megawatt electrolyzer, and this hydrogen produced in the electrolyzer can be used in three ways. Two of these ways, the first ones are the hydrogen injections to the natural gas grid. They use the hydrogen in up to 10% for the natural gas CHPs, and they use it up to 5% for the normal grid for the households. But the hydrogen can also be stored in a hydrogen storage, and then we can use it in a hydrogen CHP to produce electrical energy when it's needed. And this hydrogen CHP is shown here on the right side. It's the green container. And in the next 3 slides, we're going to have a closer look at some of the highlights of these hydrogen CHP. So what is the engine technologies that enables the hydrogen, the use of hydrogen? Especially it's the gas injection. Because if we want to burn hydrogen, we cannot use an external gas mixer. The gas mixture between hydrogen and air, it would be much too dangerous because of the high flame velocity of hydrogen, and so we need a gas injection. And we decided to use a port injection, so it's not directly into the cylinder. It's an external mixture formation, but close to the cylinder. This is a big opportunity for the Hadbjerg plant because then we need much less pressure than we would need in a direct injection. And the second highlight on this engine is that it's a dual fuel engine. We can use hydrogen and natural gas. So this enables the utility in case of if the hydrogen storage is empty, then the engine can still run on natural gas. And the engine doesn't have to be stopped for this switching. We can make the mixture while the engine is running and switch slightly to natural gas. In the last step, let's have a look at the environmental compatibility. Because as you know, it's still an engine, and of course emissions are a big deal. And on this slide, we have an overview about the NOx emissions concerning the lambda. And the red line is for natural gas, and the blue line is for hydrogen. And what we see here is that if we use hydrogen, we have a very wide operating range, operating window with very high lambdas, without emission failures, because of the low emission energy of hydrogen. We can burn it very lean, and this enables the engine to run on very, very low NOx emissions. So it's very environmentally friendly. Yeah, and in conclusion, we think that the cogeneration with its efficiency can support the new renewable energy, and it can be enable the gap between the energy consumption and the capacities of our ecosystems. So thank you for your kind attention, and I'm very curious on your questions in the questions and answer session.
Thank you, Stefan. Just a reminder to everyone on the webinar, there will be an opportunity for a Q&A session after the next 2 speakers, and you can use the chat function to pose your question. I have a colleague on standby that will collect the questions and share them with the 3 speakers. So the next speaker is from Cenertech, Günter Grosch, who will talk about stationary fuel cells in use of buildings. Bear with us for one moment as we switch presenters and presentations. Thank you, Günter. The floor is yours. You're on mute. Günter, your mute function is still on.
Okay.
We can hear you now. Thank you.
Yeah. Sorry for the looking not to you, but to my presentation. It's on the second terminal. So I'm Günter Grosch. I'm working at Cenertech. It's a part of the BDR Tamer group, all over Europe working company or concern. And I want to present you a little the things about fuel cell in use cases of homes. And the energy cost of a four-person household is what you can see in a normal house. Annual energy costs hardly the same for heat, electricity, and for the car. It's, I think, typical for Germany, about 1,500 euros each of their energy sources. And at all, you need for the heating and hot water 34% total energy costs, and electricity and car makes this is 65.8%. In total, it would be 4,675 euros a year, which you need for energy costs. So let's have a look on what can be done when you use such as pellets, heat pumps, or solar heating, which have only the impact on the energy costs of 34.2%. And that would mean that you can take the heat out of this and make savings on that. That is about 30% of the heating you can save with this renewable energy producers. And the cost at all would only be 10% less costs of your energy. Let's take a look to the MICRO-CHP unit when you would take this into this view of the four-person household. Then it would be the same at all, but you can use a fuel cell MICRO-CHP as an impact on all three sectors: heat, electricity, and the car. And this would reduce the costs of total costs by 30%, not only the heat. And therefore, heating with gas, generating electricity when heating and driving with electricity. This the numbers show you that it's the best way at the moment which you can take to save most of your energies in your household. On the move with a fuel cell MICRO-CHP system, e-mobility generates additional power demand. This power demand can also be provided at home at low cost by generating your own electricity. The provision of the high energy requirements, 40 up to 50 kilowatt hours, can best be achieved in combination with a fuel cell MICRO-CHP in this stage. I will underline this with the two case studies, what we have from our customers. The first is a building built up in 1996. It was a semi-detached house, or is a semi-detached house, with a living space of 135 square meters and 4 inhabitants. The energy data are from 2015 and 2016. In 2015, it was before changing the energy system, a gas condensing boiler which consumed 13,849 kilowatt hours, and the electricity demand was about 5,000 kilowatt hours. Then they built in as a DAX Inogen system from us in 2016, and from that time on, the gas consumption is 18,000 kilowatt hours a year, and the electricity from the utilities is only the half, 2,520 kilowatt hours. That saves 850 euros a year in this household, and they are very pleased to have done this decision. I will come later on the motivations, how the decision was made. The next case study is then a semi-detached house, also constructed in 1963, and living space of 130 square meters. Windows and doors are already energetically renovated, and this was done by energy consultant who told them, yes, this would be good to do this first. Also, roof insulation would be very good, not necessary brick wall, it's okay. What he has then decided was not to do the roof insulation. He wanted to install the fuel cell heating system. He has taken a fuel cell with a peak load boiler, also integrated in our system, and a fresh water station using the flow-through principle. So Legionellas have no chance in the system. He also added a battery storage of 6 kilowatts. And then the energy data before he changed his heating system was oil boiler who needed 2,500 liters a year, and his electricity demand was 3,100 kilowatt hours. With the new DAX 0.8 system, the fuel cell MICRO-CHP, he only needs 1/3 of gas to produce his heat and power. And the electricity grid purchases is about 1,200 kilowatt hours. It's only an assumption because it's not 1 year running the system, because it was installed in November 2019. And the amortization years are calculated to 12 years. The next steps of this guy who is a technical freak, I would say, is doing the roof insulation and put on PV to support also the DAX 0.8 in summer times when not so much heat is needed, only hot water, not heating. And when the next car change will occur, then he will take an e-mobile to also support his idea of a new energy world. Now you can see the motivations of the reasons of the decision to buy such a system. The energy efficiency and the climate protection was one of the main reasons. No unnecessary waste of energy, no more oil to store in the sealer, fuel of the future, let's say hydrogen, inspired by new technology. Ordinary boiler only causes costs, reduction of electricity costs, independence from power supplies, 10-year service package, no fear that the system will break and cost additional money, and state funding also on the European level. And one of his key sentences was, "We have 2 children and would of course like to dedicate them something what is valid for the future. Thus, energy efficiency and climate protection are especially important to us." Yes. And my last slide will show you the benefits for the buildings. It's electrical efficiency, the overall efficiency. Let's say the standard of heating is A+++ and also of domestic hot water. The fuel cell MICRO-CHP can ensure particularly low heating costs by producing their own power self-directed. The owners of the building are one step closer to being independent from the power supply, and it's virtually silent because no rotating system. Supporting the energy system at all all over Europe or all over the world, lowest emissions, only emits water and air, largely free of pollutants, flexible use, capable of base and peak loaded power and heat supply. Flexible use of fossil fuels and renewables, as we have just heard from the 2G project in Hadbjerg, and fuel cells MICRO-CHP systems designed to utilize renewable produced hydrogen can contribute to linking the 2 sectors and carbonize their energy system. That was it from my side. I'm glad to hear some questions from your side and want to answer. Thank you.
Thank you, Gunther. Thank you for the introduction on fuel cells, as well as the two very interesting case studies of private citizens investing in fuel cell micro-CHP. We are now pivoting to our last speaker, and that'll be Christian Neve from EC Power. I apologize if I mispronounced your last name. I'm actually looking forward to this presentation because it's a presentation about how cogeneration and heat pumps work together in the case of a school in Denmark. We hear a lot about how the two technologies can potentially be competing, at least in Brussels. However, COGEN Europe sees cogeneration as a complementing technology. We heard a little bit about it from Olivier Bukele at the beginning, and so I'm looking forward to the next presentation. Christian, you have the floor. Christian's presentation is currently uploading, so we should be going in a couple of seconds. I seem to have some slight technical difficulties. At least, Christian, can you hear us?
Yeah, I see Christian is muted. I tried to unmute him, but it's not possible. But perhaps while we resolve this, we can maybe take some questions.
Yes. So we have so far two questions.
Sorry, I'm back online.
We can hear you, Christian.
Should I continue, or are you in the middle of a question?
No, we were just going to pivot to a chat, to some of the questions in the chat function. But now that you have your presentation up and running, let's continue with your presentation and then take all the questions in the chat function at the end. So the floor is yours, Christian.
Thank you very much, Hans, for the introduction, and sorry about that technical glitch. My name is Christian Neve, and I'm head of business development at EC Power. Now, cogeneration and heat pumps, win-win for Hadbjerg Skole in Denmark. What's that all about? Well, it's about highly flexible and energy efficient sector coupling at the site of consumption. And it's about security of supply and responsiveness. In our vision, carbon neutral on-site sector coupling goes hand in hand with system sector coupling. And Olivier and Stefan already mentioned Power to X, which we symbolize by this little switch. So the green gas is injected into the existing gas infrastructure along with the biogenic gases. And on calmer days, dispatchable technologies such as CHPs then make up for the low wind and solar electricity production. So just a few words about EC Power. For almost 25 years, we've designed, installed, and maintained energy centers such as the Hadbjerg Skole case, which we'll get back to. We have more than 10,000 systems in operation, and our main facility is in Denmark, where we produce MICRO-CHPs. And we have subsidiary in Berlin and in the US. So before we get to the actual case, I'd like to share a small simulation of the Hadbjerg case study. Here we follow a school building in Denmark. You can see the electricity loads hour by hour and the heat loads hour by hour. And they more or less correspond to the loads that Olivier mentioned earlier on. It's highly fluctuating as people come and go in the building. What you also can see is that the grid supplies the building, and a gas boiler provides heat for the building. This is a very common application in Europe. You can also notice the quite heavy losses that are in the building. We have the energy demand here, and we have the total energy consumption, including losses out here. Now below, you can see how the new energy center provides exact same energy flows as above, hour by hour, in a highly efficient and flexible manner. It responds exactly to the electrical load of the building, delivers that electrical load and also the heat. The center consists of 3 MICRO-CHPs, a heat balancing store, a heat pump with a COP of 3.5, and a backup boiler. What you can see is that the transmission losses and the heat losses are significantly lower than in this situation. And also you can see that the electrical load is quite relieved, the grid load at least. So this is kind of mesmerizing, so I'll just let it stay there a few seconds more. In this particular week, the overall efficiency of the system is 132%. So let's get to the case. Hadbjerg Skole is a municipal school which has seen quite a few renovation waves. It was built in 1928, and 2 expansion projects turned it into a modern school with 440 students. The on-site energy center, which consists of a CHP, a heat store, a heat pump, a boiler, just as you saw in the simulation, was built in 2017. This new energy center covers 63% of the electricity in the building. The rest comes from the grid. Naturally, it covers 100% of the heat in the building, and now only 10% comes from the boiler. The overall total energy efficiency annually is about 120%. So what does this do for the end customer? Well, with the gas boiler and the electricity from grid, the school had a carbon footprint of 113 tons of carbon per year. The end user, the municipality, has basically 2 options: buying natural gas and the general power mix from grid, or buying green certificates on both electricity and gas. With the latter option, the carbon footprint is 0. However, hour by hour, each day, what comes out of the socket is a mix of the sources that are present at that day of time. So in Denmark, there's no incentive, no economic incentive to pursue a carbon footprint of 0. So the municipality chose the general mix, so that gave a 30% reduction in carbon footprint. Also, the costs dropped 30%, which led to a very interesting payback time of about 6 to 7 years, including service and maintenance. So this is the energy flows before renovation on an annual basis. What you can see here to the right is the total energy consumption, and we use that as a reference. So all flow percentages are comparable. The mix out here of energy sources for the electrical grid refers to the year 2018 in order to prevent comparing apples to oranges in the before and after scenarios. But please look at this. This is 100%. And we can see that 8.7% of those 100% comes directly from coal. Sorry. When we look at the situation after renovation with the new energy center, we can see that the total energy consumption is now 88.5% of the former 100%. The losses dropped 11 to 12% with this new energy center. We can also see that the coal electricity share is only 3.8% now. This percentage could be even lower if real-time electricity prices or marginal carbon signals and incentives for grid export were present. Then the energy center could be even more responsive to availability and also to the climate. On-site energy centers are not new. This is a case also from Denmark with a housing cooperative. It has 16 apartments. They were built in 1999, and so was the energy center. We can also see that it was refurbished in 2018. Before it ran on diesel, and now it runs on bio LPG. So it's not new, nor is it limited to single homes or buildings. You can actually provide energy for a small community as well based on these systems. Yes, so let's wrap this up. Energy centers with cogeneration and heat pumps offer flexible and energy efficient sector coupling at site of consumption. The system efficiency can be up to 160%, whereas for individual sectors we're significantly lower, also corresponding to the figures that Olivier showed early on. And by storing green gases, wind and solar grid integration becomes unlimited. Today, electricity prices drop to 0 or become negative when it's very windy and sunny. and that's not very good for the investment in new technologies, or sorry, in wind and solar. So cogeneration and heat pumps offer flexibility and redundant security of supply. And it's an ever-increasing share of uncontrollable electricity production that we are seeing in the future. Last but not least, for the end user, the increased efficiency of energy centers and the reduced energy bill offer a very interesting investment opportunity for the end user, and also a lower carbon footprint. So what's not to like? Thank you very much.
Thank you, Christian. Thank you for a very interesting presentation. We have some time now for a number of questions. Looking to the chat function, we have 2 or 3. The first question goes to Stefan from 2G. The question is about the pilot project and how is it financed, and now and in the long term, and in your opinion, what would be the key factors allowing the replication of this good example in other contexts?
Yeah. Hello, Arthur. Thank you for your interesting question. At the moment, in the time of the research, the project is financed by the Bavarian government, but this is only by the end of this year. Then this financing ends. After this year, the project will be financed by a combination of a virtual power plant, providing positive and negative energy, so positive and negative power, and in combination, the energy is sold to the Greenpeace energy group, and because of the fact that the primary energy source is wind, they sell a product which is called the hydrogen, which is produced by the wind, is called wind gas, and they sell this wind gas. And if you produce electrical energy by the CHP from this wind gas, they sell it also as wind energy. So it's sold by Greenpeace Energy.
Okay. Thank you, Stefan. There was another question to Gunther, but he took the opportunity to answer it online himself. It was in relation to the cost of a fuel cell MICRO-CHP unit. And those of you who are not looking at the chat function, he answered it could be approximately 25,000 euros, including the installation. But there are a number of subsidies available, up to 11,000, depending on where you live. It may be a local, regional, or a national, federal subsidy in support of the uptake of efficient technologies. We have another question. This is to Christian from EC Power, asking about the possibility to have a hydraulic schematic for the CHP pump arrangement. Apparently there's some interest in how you manage the differences in operating temperatures. I don't know if you can answer that, Christian.
I do not have a schematic right now, but what we do is to preheat the water with the heat pump. So it has the heat pump makes up a base load for the building. And thereby we have a very interesting return temperature, and we can make a very high COPs on it.
Okay. Thank you, Christian. Are there any more questions? If not, I'll give everyone an opportunity. We have another 10-15 minutes to think about your questions for the 3 speakers. And in the meantime, I will give the floor to my colleague Alexandra, who will give a wrap-up from a policy perspective in terms of the renovation strategy and the role for cogeneration. So Alexandra, the floor is yours, and don't forget to ask your questions in the chat function.
Thank you, Hans. So as you have seen, there are many applications that are future-proof, where CHP can contribute towards energy efficiency, towards decarbonization of the building sector. And here we have an overview of how cogeneration can support an ambitious Green Deal. So we see that already today, cogeneration delivers 11% of EU's electricity, 16.5% of EU's heat. And as we've seen before, around 70% of the heat that is used in district heating comes from cogeneration, from high-efficiency cogeneration plants. This generates around 360 terawatt hours of primary energy savings, which is more or less 10%, 10 to 15% of EU's energy efficiency target at this stage. So that's quite significant, and we think that cogeneration can contribute even more. If we look at emission reductions today from cogeneration, we estimate that more than 250 million tons of CO2 is avoided every year thanks to cogeneration. And this is equivalent, just to put things into perspective, to the emissions of about 100 million petrol cars. But as mentioned, as we see, there's a lot of innovation and a lot of drive within the cogeneration sector to do more. So by 2030, we estimate that cogeneration can, the contribution of cogeneration can double, providing 20% of EU's electricity and 25% of EU's heat on a range of increasingly renewable energy sources and low carbon energy sources. And based on this, the new and upgraded CHP can help avoid an additional 350 million tons of CO2. And again, to put this into perspective, this would be around a third of what is needed to increase the EU 2030 target from minus 40% to minus 50 and even minus 55% greenhouse gas emission reductions compared to 1990. So actually, we are all for more ambition, and the cogeneration sector can deliver that. My slides are not quite cooperative. So as we've seen, we have a diversity of applications for buildings in the cogeneration range of technologies and solutions. When it comes to CHP for district heating, there are several benefits where these district heating networks are in place in cities mainly with high heat densities. CHP will supply efficient and affordable heat for residential areas and commerces that is delivered to customers through district heating. And of course, there's a need of investments both in the district heating networks and in the modernization of the CHP or the boiler that is supplying that heat. It produces flexible electricity, supporting the local electricity grids at times of low wind or sun. If you enable that energy system with heat storage and smart controls, cogenerated heat and power can actually be decoupled and provide even greater flexibility at very high efficiencies for the electricity system. And so with all of this combined, CHP will ensure a smart systems integration at the local level, while also addressing local pollution. What we see in some cities is that even if there's an infrastructure for district heating, many of the customers are disconnecting from the district heating networks and install individual apartment boilers, sometimes very inefficient, which also contributes quite significantly to NOx and SOx concentrations in the city. So by enabling efficient district heating with cogeneration, you are actually addressing some of that local pollution. And as mentioned, there are also on-site applications for buildings. Yeah, just apologies for my slides. It looks like they are not working. So in addition to district heating, there is on-site CHP. And you've seen quite a lot of you've seen quite a lot of examples here with the fuel cell micro CHP and also the EC Power with the mini CHP installed in a school on site. So the benefits of those is that it provides the diverse building needs via range of power to heat ratios. So depending on the technology, you can install these systems in either older, less insulated buildings or in newer, highly efficient buildings. They reduce the energy cost at end user level. They complement electric heating and electric vehicles demand by producing this flexible electricity locally and by meeting peak demand at times of no wind and sun. This is very important because we know that while the shares of intermittent renewables are increasing, there's often a mismatch between peak demand and the supply of these renewable sources. At the same time, on-site CHP will ensure the most efficient use of renewable and decarbonized gases, including the uptake of hydrogen in buildings. And they can be aggregated as part of virtual power plants to provide grid services. So it's not needed anymore to have a very large-scale power plant, centralized power plant, but you can aggregate these systems to provide grid services. So this, in a nutshell, is a slide that shows our recommendations for the Renovation Wave. As mentioned in the very beginning, buildings are very important for our decarbonization efforts. They're very important for citizens and for the economy. And we think that Renovation Wave must be ambitious across these different dimensions that are shown here. When it comes to energy efficiency, we must have energy efficient buildings, that's no question, but we must also apply energy efficiency across the whole energy supply chain and across all energy sources. So efficiency of demand must be complemented by efficient supply solutions. And in that case, CHP is a key building solution that should be taken into account. Then we've talked a lot about the electrification of end use. In this case, the electrification of buildings is seen as one of the key solutions to decarbonize and improve the efficiency of buildings. Yet, in order to ensure that, we must make sure that buildings are electrified in a smart way. So we must have robust criteria to promote renewable and efficient electrification of buildings. As you've seen in the case study by EC Power, by coupling CHP with heat pumps, you actually manage to increase the share of renewables, decrease total energy demand, and while also managing to relieve pressure on electricity grids. So I think the synergies between solutions like CHP and heat pumps or CHP and electric vehicles, these synergies must be explored and promoted. Then moving on to renewable and decarbonized gases, we see that there's a big discussion and increased recognition of the role of the gas networks in decarbonizing the economy, including buildings. And so we want to see this promoted across all applications. Also to address the decarbonization of heat in buildings, which we've seen has quite a few challenges. And when these renewable and decarbonized gases are available, we must prioritize the use of CHP to maximize their efficient use. And then lastly, energy systems integration. This is, from our perspective, a key way of ensuring our economy is zero carbon by 2050 in a cost-effective way. So in order to achieve this, we must have long-term planning at the local level to integrate the infrastructures that are near the consumer. So local distributed gas grids, the district heating networks, and also the distributed electricity networks must all come together and be optimized from an operational point of view, but also from a long-term planning perspective. And so from this perspective, we must remove the barriers to such solutions that enable that energy systems integration, like cogeneration, like district heating, and do that efficiently. So with that, I thank you for your attention. I will hand the mic back to Hans.
Thank you, Alexandra. This is also an opportunity for everyone online still to ask questions to Alexandra as well in terms of her presentation from a policy perspective. I do see that we have one final question on the chat function, and this is to Stefan from 2G. Do you have any figures about the electrical efficiency of hydrogen CHP?
Yeah, thank you for your question, Olivier. The electrical efficiency at the moment is about 39%. From the development, we know that we can still increase the power, and by increasing the power, the electrical efficiency will also rise. So at the moment 39, but our goal would be about 40 to 41%.
Okay. Thank you, Stefan.
Yep.
I don't see any other questions. So what I'd like to do now is to remind everyone that this session, this webinar has been recorded as part of our Power and Heat Boost series. We will make it available on the COGEN Europe website in the Power and Heat Boost web pages. You will receive an email shortly with a link to the recording as well as the different presentations. And feel free to share that with your colleagues and partners, etc. This will be the last Power and Heat Boost webinar before the summer break, and we'll start up again in September with our next segment. That is not to say that we are closing up. In fact, we have quite a few other different events via different platforms in terms of webinars in June and July. For those of you who would be interested, COGEN Europe is part of a group of different organizations, including the Covenant of Mayors and SEDEC, as part of the Sustainable Energy Week that begins next week. So COGEN Europe with SEDEC and the Covenant of Mayors, we're organizing a webinar this Thursday, the 18th of June, between 1:30 and 3 o'clock. And it'll be focusing specifically on district heating, working towards local sustainable solutions. We're very pleased to have the chair of the European Parliament's Industry and Energy Committee, Christian Bouchoy, an MEP, and then we have a number of different panelists, including companies from Veolia, the city of Rotterdam, and also we have someone representing the European Commission, the Energy Directorate. So if you want more information, please contact COGEN Europe. The information is also available online via the Sustainable Energy Week. That having been said, thank you all for your attention and the interactiveness and your questions. And we look forward to speaking to you via different platforms, may it be webinars, at least for the foreseeable future, and hopefully we will be able to speak face-to-face sometime soon. So thank you, and I wish you all a very pleasant afternoon.